Thank you, mayors. We're going to move right ahead now. We're going to have a presentation about hurricane tracking by the representative of the National Weather Service Charleston office, Carl Barnes. Mr. Barnes is a meteorologist. He has his BS in meteorology from NC State in 2011. So he's a fairly recent employee with the National Weather Service in Charleston. Mr. Barnes?
All right, thank you very much. It's really a pleasure to be here. I appreciate the invitation as always. This is really a great event, great participation, really well organized. So it's great that you get to do this, and we actually have this year something to review. Last year it was all kind of speaking in hypotheticals. So we'll just take a quick look at the science of hurricane forecasting. It's something that really gets me excited. So when I was asked to talk about the science aspect of it, man, that was just great because to get to talk about that at preparedness is really a treat. So two main aspects to forecasting a hurricane: the track of the hurricane and the strength of the hurricane. There are a bunch of other secondary aspects, but those are the two main things. Track forecasting. I'm sure you've all seen the spaghetti style plots where you have a bunch of lines going all over the map and it's saying, oh, this is what one model says, this is what another model says. And kind of a little explanation with these, you'll see that at the beginning they're all pretty good because they use observations to tell where the storm's at. We have the hurricane hunters that fly out in the airplanes and sample the storm. We also will take local measurements. We'll do weather balloon releases twice as frequently as normal, basically on the whole East Coast and across much of the South to try to sample the environment that the hurricane might be going into. So we have a pretty good idea of what's going on at the time. But as we get further out, there's much more uncertainty. So that's why you usually see this spread in the models. The storms will naturally move northward and to the right. But the main thing that determines the direction they go is high pressure. High pressure deflects storms. So forecasting that high pressure is key to forecasting where the storm's going to go. The other and much more difficult thing to forecast is the intensity. Much, much more complicated to forecast intensity. We have very few observations out over the ocean where the storm is typically developing, and so it's harder to know exactly what's going on at the time, which makes it thus harder to know what's going to be going on, out in further time frames. A few things that are key for forecasting hurricane intensity: the vertical change in the atmospheric winds, known as wind shear. Higher shear makes it harder for a storm to really strengthen. The amount of moisture in the atmosphere, obviously, you usually see hurricanes, or you always see hurricanes form in the tropics where there's plenty of moist, warm air. And you also have to have warm water temps, which around here is really not a problem in the summer and the fall. And then also it goes hand in hand with the track. You have to have a good track to have a good intensity forecast. So the track forecast is usually good. The intensity forecast is typically much more uncertain. So then we take that information that comes from the models, and it's first basically reviewed by a forecaster or forecasters at the National Hurricane Center, which is down in Miami. They put out the official National Hurricane Center track and strength forecast, and that's after they basically use their forecaster knowledge to compile what information the models is giving us. And so on the left is what you'll typically see. Sorry, I kind of squat down in case you need to see everything. So we have the track and the cone of uncertainty. A little tidbit about the cone of uncertainty: a lot of people don't realize this. It doesn't change from storm to storm. It's based on basically the last 10 years, an average error of the storm. And they can say, based on the storms that have happened in the last 10 years, this is kind of an average error that you can expect it to typically stay within this cone. We also, on the right, have something that to us is more meaningful. It's the probability of wind impacting any given spot on the map. So this is important because this takes into account something that the cone of uncertainty doesn't. This takes into account the size of the storm and the size of the wind field, so how far the strong winds are from the center. So this is a good map because you can just look at your location on this at any given forecast update and see what your probability of receiving those strong winds are. We then take the National Hurricane Center forecast for the storm track and intensity, and we tailor it to our local area. So the Charleston Forecast Office, which is located up at the airport in North Charleston, we cover the Charleston metro area, the Savannah metro area, and kind of the surrounding areas around those. So we have a pretty specific region that we're concerned about, and because of that, we really get to hone our expertise and understand the local effects of what goes on. And then with that, we take that basically numbers forecast that the Hurricane Center gives us of this is your wind speed, this is the storm direction, storm speed, and we try to translate that into impacts to work with the emergency managers, to work with Charleston County Emergency Management. We work really closely with the SCEMD, who's going to be talking next, and we try to give them the best possible forecast so that they can make the best plans possible in terms of evacuations and a bunch of the other stuff that we're going to be talking about for the rest of today. So we're the ones who really bring it down from the national level at the Hurricane Center to the local level. The big topic of the day, Matthew. So how were the forecasts during Matthew? The generation of Matthew was actually really well forecast. It was predicted to generate 138 hours before it actually became a hurricane. That was way out in the middle of the Atlantic, so that doesn't really have an impact on anyone, but we can't say we didn't see the storm coming. What we can say is that the actual track gave us some problems in the longer term. So within about a day, we were able to pretty well tell where the storm was going to go, 24 hours out from any given time, which is typical. Typically in the closer time ranges, you're able to have a more accurate forecast. But for Matthew, we actually did even better than normal. In that 3 to 5 day range, which is when evacuation orders need to be typically decided upon and a bunch of other decisions need to be made, that's when we had a little more trouble. So it might be a little difficult to see on this graph, especially for people in the back, but this is all of the forecasts overlaid with the actual track of Matthew. The track is a red line, so it's kind of hard to see the red line, which is good. That means that our track forecasts were covering the actual track, which is good. But you can see a number of the forecasts from when the storm was still in the Caribbean actually took it well off the coast, almost taking it directly north, staying pretty far off of our coast. And we had some, variability in what the models were telling us ahead of time. So we actually had a situation where we were working with the state. We have another office in Columbia that works really closely with the state, and they were trying to determine, evacuations, whether it was going to be necessary, what kind of timeline to do. And when they were working on that, the storm actually started trending. The forecast started trending further off the coast, and so it was kind of a hairy situation because decisions were having to be made, and then all of a sudden, and this was after the governor had already started, talking about the possibility of evacuations, so that it might be needed. It was all of a sudden a situation of, well, do we need to go backwards a little bit and say, never mind, or what do we need to do? And so we tried to communicate to the state that, the track could just as easily shift right back toward the coast. And fortunately, well, I'm not going to say fortunately, but that is what ended up happening. Fortunately, the governor and the people at the state level are very, very good, and they totally understood that the threat was still there, even though the track was looking better. And of course, it is what ended up happening with the storm hugging the coast all the way up. The intensity for Matthew was also generally pretty well forecasted. Sorry, this is a little bit of a busy graphic, but the actual blue line is the trend of the intensity. So you can see that there was that one area that's outlined in the red box. That's when it went through rapid intensification down in the Caribbean. That was not so well forecasted, but then as it started approaching the southeast coast, we actually did a pretty good job. We were forecasting it to be a weak 2 or strong category 1 as it came through here. It ended up being a category 1. So with that, it was pretty good, but obviously the center of the storm and how far off the coast that was also depended on what actual wind speeds you saw at any given location. And so on the left, we have the actual track. We did make landfall. The storm did make landfall near McClellanville, and it made landfall as a Category 1 hurricane, and that was about 11 a.m. on, I believe it was October 8th. So this was the first hurricane since Hazel to make landfall north of Florida during the month of October, and Hazel was 1951. So a few of the wind speeds that were observed around the area, On Folly Beach, we had wind gusts up to about 75 miles per hour. Up at the airport where we were about 70 miles an hour. But then down just to our south, Hilton Head's been mentioned a couple times. They had a wind gust of 88 miles per hour when the storm was still approaching, and then their wind sensor went out. So I'm sure they gusted even higher than that. We have a buoy that's located just kind of off the coast, off St. Helena Sound, and that gusted to 83 miles per hour when the storm was still about 6 hours away, and that buoy unfortunately also went out. So we actually certainly got higher winds than were actually observed because a lot of our sensors went out. The highest that we did have observed along kind of our stretch of coast in the southeast was down at Tybee Island. They had wind gusts up near 100 miles an hour, 96 miles an hour for a brief period of time. And then the final threat that we're looking at, this actually ended up being the biggest killer in the United States for Matthew, was the freshwater flooding, so basically rainfall flooding. There were 34 deaths directly attributed to Matthew. 24 of those were in North Carolina, and 23 of those were from freshwater flooding. In our area, we got a pretty large swath that came right over us here in Charleston County of 10 or more inches generally from the storm. We ended up seeing, even along a lot of coastal areas, the freshwater flooding was actually more of an issue than the saltwater flooding. And from a combination of salt and freshwater flooding, we had 1 million structures either impaired or damaged. And total from, I guess they're actually still calculating the damage estimates. One more thing that I forgot to mention on this slide, on the right is storm surge. So we generally assessed that we had as high as about 3 to 5 feet of storm surge for pretty much all of our section of the coast. As was mentioned before, we got fortunate that Matthew didn't hit at high tide. Down in Savannah and kind of areas just a little bit south of Savannah, it did hit at high tide. They saw a record all-time high tide there. Here, Matthew was one of our top, but certainly Hugo is the highest that we've ever seen recorded. So I believe Matthew was our second highest water level, and it really still had feet to go before it was close to what Matthew did. This was the first time that we were able to issue one of our products. We have a storm surge watch and warning that comes out now. That's going to be issued whenever we're expecting 3 feet or more of inundation. So that's salt water above ground level. We're going to issue a storm surge watch and a storm surge warning to go along with whatever hurricane or tropical storm watch and warning, kind of just to make sure that we accentuate that the storm surge is just as big of a threat, or oftentimes more of a threat than the actual winds. So at this time, I can open it up to any questions that you guys have for me. Additionally, I'll be back there all day, so if you just want to come up and talk to me one-on-one, I'd be glad to help you out with anything. We obviously do a lot more than just the forecasting aspect, but I kind of wanted to cover that today, especially since Matthew is still hot on everyone's mind. Yeah.
Is there any probability research that since we just had a hurricane, we're more likely or less likely to have another one, or is that impossible?
So we do have recurrence intervals saying that, a storm like Matthew, I believe it would happen something on the order of an average of once every, I think it's 8 to 10 years, somewhere around there. But that doesn't mean from one year to the next it's any more or less likely, because before Matthew, obviously we went 25 years or so since Hugo. So no, unfortunately that does not mean we're any less or more likely. It gives no indication of what this hurricane season would be like. And the hurricane forecast from NOAA, we're looking at just slightly above normal for hurricane occurrence. Doesn't mean for landfall or whether it's going to affect us or not, but just overall for this season, we're looking at slightly above normal numbers. Yes, sir.
With the discrepancy in models, what are your lessons learned in terms of culling through your available models and prioritizing those that are most accurate over a certain interval of time?
Good question. So for Matthew, we found that, and you've probably heard this before, it actually grabs a lot of headlines. The European model beat the American model again for Matthew. And actually the Europeans have a model that they all work on together. Also, England has its own, the United Kingdom has its own model, which also beat the American model. So that's not always the case. That's the challenge, is that the European model typically does better. It typically does the best until it doesn't. So it's, that's really the challenge in forecasting. We'd love to be able to say, okay, it did better this storm, so we'll always use it, but unfortunately it's not that easy. But they definitely did learn lessons. It's all about being able to pick up on these patterns in the models. And unfortunately right now the European model is basically beating us most storms. But we realize that, and because of that we rely more heavily on it. But every storm we go back, we do a really thorough review and we see what we can learn. And in this one we picked up a couple things that the European model just resolved better, basically. Yes, absolutely. So the question is a track that hugs the coast like Matthew did less typical than a direct landfall perpendicular to the coast, which those of you familiar with Hugo, that's basically exactly what Hugo did. Honestly, I do not know the answer. I would say that a track where it's coming more directly on coast is probably more likely. But this track where it kind of just rides up the coast has been seen before. Hazel did something very similar. And in terms of which one's more likely, it's tough to say. In terms of which one does more damage, a track bringing it directly on the coast will do a lot more damage in a very focused area. Something like Matthew, we had significant damage from basically Cape Canaveral all the way up to the Outer Banks of North Carolina. So it makes a difference. Yes, ma'am. Oh man, I could go for hours about that. The one big thing is the power of the computers. The Europeans have a more powerful computer than we do. We are working on improving that, just like they're working on staying further ahead of us. So they're continually adding more power to their computer, and we're continually adding more, and we're trying to play catch up, but they just keep staying just a little bit ahead of us. We also different ways that they incorporate observations and different resolutions within the model make a big difference. So the question is, why did, since it essentially hugged the coast the whole way up, why did they end up getting more damage down Tybee and Hilton Head than we did up here? And there's natural cycles that the hurricane goes through. So the winds were a little bit stronger with the hurricane down there than they were up here. Also, the eye wall was a little bit larger down there. It hit high tide, so some of their damage was from more storm surge flooding than they had here. But there's also a lot of very small scale effects that go on in the eye wall that we don't totally understand. So there's a possibility that there's basically a bunch of very small tornadoes that occur within the eye wall. And when we were doing damage surveys down around Beaufort and Hilton Head and Tybee Island, we found that there would be one block, there would just be hundreds of trees down. The next block would almost look untouched. So we think there's really small scale effects that go on inside of the eye wall that unfortunately we just can't explain at this time. So with that, I'll probably go ahead and cut off questions. Please, anyone who has more, feel free to see me during lunch or anytime this afternoon. And I thank you very much for letting me talk.